Comet 3 I/Atlas represents one of the most remarkable discoveries in modern astronomy, offering scientists a rare and fleeting glimpse into material that predates our own sun and originates far beyond the boundaries of the solar system. As only the third confirmed interstellar object ever observed passing through our cosmic neighborhood, it immediately captured global scientific attention when it was discovered in July 2025. Unlike objects that are gravitationally bound to the sun, Comet 3 I/Atlas follows a hyperbolic trajectory, meaning its visit is a singular event. It entered the solar system from deep interstellar space, accelerated around the sun, and will eventually depart forever, never to return. This brief encounter provided researchers with an extraordinary opportunity to study pristine material formed in an entirely different stellar environment, preserved for billions of years and largely untouched by the processes that shaped our own planetary system. What sets Comet 3 I/Atlas apart from ordinary comets is its highly unusual physical and chemical behavior. Traditional comets are often described as dirty snowballs, composed mainly of ice, dust, and rocky material, typically protected by a hardened crust formed through repeated passes near the sun. In contrast, this interstellar visitor displayed characteristics that challenged long-standing assumptions about cometary bodies. Observations revealed that Comet 3 I/Atlas exhibits properties associated not only with icy comets, but also with processes resembling volcanic or magma-like activity. This does not imply molten rock in the traditional sense, but rather energetic eruptions driven by volatile chemicals and internal pressure, producing effects that closely mimic volcanic outgassing. Such behavior had never before been observed on a small interstellar object, making this comet an unprecedented subject of study. Spectroscopic analysis revealed that the comet's composition is exceptionally rich in carbon dioxide, water ice, carbon compounds, and various metal-bearing gases. These findings strongly suggest that Comet 3 I/Atlas formed in an extremely cold, chemically rich region far from its original star. In such distant environments, volatile compounds like carbon dioxide and other frozen gases can accumulate in large quantities, remaining stable for billions of years. The abundance of these materials implies that the comet originated in the outer reaches of an alien planetary system, possibly beyond the equivalent of our Kuiper belt or even farther, where temperatures are low enough to preserve fragile compounds that would otherwise evaporate or chemically alter closer to a star. One of the most striking features of Comet 3 I/Atlas is the apparent absence of a thick, protective crust. Most comets that originate within our solar system develop an insulating outer layer over time due to repeated heating cycles as they orbit the sun. This crust acts as a barrier, regulating sublimation and limiting the release of volatile materials. However, because Comet 3 I/Atlas is making its first and only close encounter with a star like our sun, its surface remained largely unaltered and exposed. This naked, ancient icy exterior allowed sunlight to penetrate more deeply, triggering violent reactions beneath the surface as the comet warmed rapidly for the first time in its existence. As solar radiation heated the comet, the carbon dioxide-rich icy layers began to sublimate directly from solid to gas. This process caused pressure to build beneath the surface, much like steam accumulating beneath ice. Instead of melting rock or producing lava, the comet responded by ejecting jets of gas, vaporized metals, and icy particles with immense force. These eruptions were so powerful that they produced a noticeable brightening, indicating that large portions of the surface may have fractured almost simultaneously. This widespread fracturing suggests that the comet's outer layers were structurally fragile, unable to contain the intense internal pressure generated by rapid heating and chemical reactions. At the heart of this violent activity lies a fascinating chemical process. Scientists propose that when small amounts of liquid water interacted with microscopic grains of iron and nickel embedded within the comet, an exothermic reaction occurred. This reaction released heat and produced hydrogen gas, further increasing internal pressure. As the gas accumulated beneath the surface, it sought pathways to escape, eventually bursting through cracks and weak points in explosive jets. This mechanism provides a compelling explanation for the comet's unusually high levels of carbon dioxide emission, which far exceeded what is typically observed in solar system comets of similar size. Another extraordinary characteristic observed in Comet 3 I/Atlas is the presence of an anti-tail, a bright streak of material that appeared to point in the direction of the comet's motion rather than trailing behind it. In some cases, anti-tails can be explained as optical illusions caused by viewing geometry and the distribution of dust particles. However, in this instance, the anti-tail appeared unusually early and with remarkable clarity, suggesting a physical process rather than a simple perspective effect. Researchers theorize that powerful cryovolcanic jets propelled large icy particles toward the sun, forming a bright beam that resisted immediate deflection by solar radiation pressure. These sunward-directed jets imply that the forces driving the comet's activity were exceptionally strong. Carbon dioxide-powered eruptions appear to have accelerated material with such intensity that even the sun's outward pressure could not instantly reverse its direction. As the expelled icy fragments traveled closer to the sun, they gradually evaporated, creating a luminous, forward-pointing feature unlike anything previously documented. This phenomenon underscores just how energetic and chemically driven the comet's internal processes were, highlighting the diversity of behaviors possible among small bodies formed in different stellar environments. The implications of discovering such a comet extend far beyond a single object. Until now, cryovolcanic activity was primarily associated with large icy moons, such as Europa or Enceladus, where tidal heating and subsurface oceans drive geyser-like eruptions. Comet 3 I/Atlas demonstrates that similar processes can occur on much smaller bodies, provided the right chemical conditions exist. This finding expands our understanding of where and how cryovolcanism can arise, suggesting that it may be a common phenomenon in cold, chemically rich regions of planetary systems throughout the galaxy. Although the comet never passed close enough to Earth for detailed, high-resolution observation, the data collected from afar proved invaluable. By analyzing its light, gas emissions, and dynamic behavior, scientists were able to reconstruct its composition, internal structure, and likely formation environment. These insights offer a rare window into how other planetary systems form, evolve, and ultimately eject icy debris into interstellar space. Comet 3 I/Atlas serves as a tangible reminder that our solar system is not isolated, but rather part of a vast cosmic exchange where material from distant stars can occasionally wander into our vicinity. Ultimately, this interstellar visitor has reshaped scientific perceptions of what comets can be. Once thought to be relatively simple, inert remnants of planetary formation, comets are now understood to be dynamic, chemically complex bodies capable of dramatic and energetic behavior. Comet 3 I/Atlas, acting as a natural time capsule from another solar system, has challenged long-held assumptions and opened new avenues of research into the chemistry, physics, and diversity of small bodies across the galaxy. Even in its brief passage, it has left a lasting impact on our understanding of the universe, proving that profound discoveries can arise from objects that appear only once and vanish forever into the depths of interstellar space.